commend the organisers for the way they've actually put these together, because they go in sequence quite nicely. So what I'm going to talk about is to water and trying to deliver water in a way that stimulates productivity to fuel the base of the food web, rather than a lot of the focus being on the top end of the trophic level right at the outcome. So the way that, or the capacity to deliver environmental water around the world revolves around these four basic premises. So it's the amount of water that's actually available within the system, the ecological needs and the ecological response to the delivery of that water, the system constraints. So what is it about the behaviour of the system and the way the system needs to be operated that constrains the amount of water that you can deliver at any particular time, and the social and economic ramifications for delivering that water instead of delivering it to agriculture or making that water available for agriculture. And what we see in the Murray-Darling Basin is that there is a very large focus on delivering water to the metrics of environmental water requirements. And these metrics include the magnitude of discharge, the duration of discharge, the timing, and something that's becoming increasingly evident is the amount of area of floodplain that's inundated by an individual management action. These two plots, the plot on the left shows, so the timeline on the bottom here is 2008 to 2015, and what the data is showing is the modelled natural discharge at Lock 5 if the catchment hadn't been developed. So this is basically through a mathematical model, and what it shows is there's a very large variation in discharge through every year associated with catchment rainfall and catchment. The plot on the right-hand side shows for exactly the same period, so from 2008 to 2015, the actual flow that came down the river during that period. And so if you look at the discrepancy in magnitude between the two events, you can see why there's a very large emphasis in environmental watering on reinstating discharge into the Murray for environmental outcomes. And this is a well-justified objective of environmental watering. However, what this tends to overlook is one of the main impacts of catchment development that has occurred throughout the river. So this plot on the right-hand side, so I'm going to be using the pointer and I'll try and concentrate on the slide set on the right-hand side. So this plot shows the structures that have been built along the River Murray over the last 110 or so years, and with distance along the bottom. And this scale goes from 0 to 550 kilometres in 50-kilometre increments. And what you can see is in the upper and middle Murray, there are very long distances between the structures, 50 to 500 kilometres between structures. And so these reaches flow as pseudo-free-flowing reaches, as water level varies with discharge. However, when you get into the lower parts of what we call the lower Murray or the lower Murray-Darling, from Lock 10, 11 at Wentworth, where the junction of the Murray and the Darling, down to the SA border and down from the SA border to the lower lakes, there are a large number of structures, and the average distance between these structures is only 63 kilometres. And so these reaches do not function as free-flowing reaches, and those weirs have a very large number of ecological impacts, including changing the velocity, changing the lateral and longitudinal connectivity of the system. One of the most dramatic things that we can see very easily is the impact that it has on the disconnection or the connection between discharge and water level. This overlay on the plot on the left, so the black line is showing flow in the River Murray under modelled natural conditions from 2008 to 15, and the red line is showing modelled natural water level. And you can see from this plot there's a very tight relationship between discharge and water level under modelled natural conditions in the river. This plot on the right, I'll overlay the same conditions for the same period. So this is 2008 to 15, and we see that even though the discharge is muted, there is still a variation in discharge. But this red line up here shows the water level upstream of Lock 5. And so you can see that the construction and operation of the weirs has created a very strong disconnection between discharge and water. This has a number of severe ecological impact. One of which is that the water levels are artificially much higher than they normally would have been at equivalent flows. And this focus on reinstating discharge overlooks this disconnection or downplays the role of the disconnection and the role of hydraulics in ecological outcomes, and the role of productivity as a driver of ecological outcomes for high trophic levels. So what are the dominant management levers that are available? So they are increasing river discharge, and manipulating water level using constructed infrastructure. So we've already heard a bit about this today, about using weirs, and a little bit more about using new and proposed infrastructure to manipulate water level, to deliver water to environmental assets to achieve outcomes. The ecological challenges that we face with this is that there is currently a large focus on management actions at the site scale, but with an expectation that those site scale actions will improve the sustainability and resilience of the system at the landscape scale, which is the scale at which ecosystems actually operate. And there's also a temporal challenge in looking at those outcomes that occur in response to a single event. So we're talking about things like primary productivity responses, the condition of attributes such as trees or fish, spawning of fish or germination events for understory and overstory vegetation. And those outcomes will only occur in response to decadal scale changes of regime. So we're talking about things about improved habitat and carrying capacity, the survival of recruits that spawn or recruit from individual events, and long-term changes to population demographics, replacing the trees that have been lost over the last 50 years of poor conditions, and essentially the long-term sustainability of the ecosystem. So what I'm going to talk about for the rest of the talk is largely about primary productivity responses. One of the projects we've been working on that was talked about earlier was using weed pool manipulations to influence biofilms. So the colonisation process for biofilms, if you have a bare substrate, is to go from bare substrate to be rapidly colonised by bacteria and fungi, and where there is sufficient light to support photosynthesis, you have diatoms and unicellular algae develop, and if you have stable conditions, you eventually progress towards having the dominance of filamentous green algae and cyanobacteria. In a system where water levels rise and fall on a regular basis, the desiccation process will lead to the biofilms being dried out, and you essentially have a return to bare substrate. On the rising limb, you have these bare substrates being colonised through this process, and areas where the substrates were already submerged and there are biofilms already existing. That deep submergence, if it takes the substrate out of the light regime or out of the euphotic zone, enough light to support photosynthesis, the biofilm will revert back to being dominated by bacteria and fungi. In stable weir pools, or in weir pools where there are stable water levels, what you tend to see is a succession towards filamentous green algae and cyanobacteria, which is not a desired outcome. It's a low quality resource for the food web. And it is intended that weir pool manipulations would help to reset these processes. So you would expect that weir pool raising would reinstate deep submergence and drive biofilms back to being dominated by bacteria and fungi, and that a weir pool lowering would reinstate the desiccation process. And the overriding hypothesis is these biofilms that are exposed to a variable water level will be more diverse and have a higher nutritional value for the food web. This schematic just shows the study sites we've been using. So this is Lock 2 and Lock 3 and Lock 4 moving, so we're moving upriver. And where the red arrows are our main impact sites, and the blue lines are our reference sites. They're not true reference sites because the river conditions are different at every single site. So they're actually independent treatments, but the treatments undergo different regimes. At Lock 2, as we've already heard, there was a 50 centimetre weir pool raising, and so we would expect water levels to increase here and increase here. At each site, we're looking at two. So we have biofilm blocks. These are blocks of wood. They're about the size of my hand. They're constructed of river red gum. There's one set of frames that are fixed at a set height. So as water levels increase, those blocks see a change in water level. And another set of blocks that are established on floating frames. So as water levels change, the frame moves down, and those blocks see effectively continue to see a stable water regime. Part of the experiment we wanted to see was a 50 centimetre change in water level sufficient to drive a change in biofilms? And this apparatus here is a good old trusty aluminium ladder with some blocks bolted onto it down through the water column. So this is our surface block, and this is the sort of change in water level we expect to see from these weir pool manipulations. This plot here shows the blocks. So there's this top one, this is a box and whisker plot. So the box encloses the 25th to 75th percentile of data, and the whiskers on the end enclose the 5 to 95th percentile data. You can see at the surface This is our autotrophic index, which is an index of how much of the biofilm is comprised by photosynthetic organisms. And you can see that as you move down through the water column, there's a change in the autotrophic index. So the change in water level that can be achieved through these weed pool manipulations is theoretically enough to drive the sorts of changes that we're looking for. This is the data from our particular sites. So I'll just walk through these. So there's a date along the bottom. So this is from August 2015 through until February 2016 along the bottom. The blue line in each plot represents the depth at which the fixed biofilm blocks are established, and the red line is the actual water level at the site. So you can see at Lock 3, where there was no manipulation of the pool, water level was continuously stable. At Lock 2, this is the actual weed pool manipulation, and you see that reflected in the tailwater of the Lock 2 to Lock 3 reach. So this is in the Lock 2 reach, but downstream of Lock 3, and you see a change at Lock 4. These two slides show some of the indicators that we use. So the plot on the left is total mass, and the plot on the right is chlorophyll A. So just put these red lines around here, it makes it easier for you to see the pairings of data. So what you can see is that upstream of Lock 2, where the weed pool manipulation occurred, there is a small difference between the mean mass between the fixed frames and the floating frames. So that suggests that the weed pool manipulation has altered the amount of mass that's accumulating in the biofilms. And the same with the chlorophyll. There is some difference in chlorophyll between the fixed and floating frame at that main treatment site. What does come out of the data, though, is that there are much, much bigger differences in mass and chlorophyll at the sites that are downstream of the weirs. And so this suggests that there's something in the weed pool manipulation that's not actually driving the change. It would be very easy to expect that this is due to the magnitude of change in water level. But if we just skip back. So this is a manipulated site, and you can see this is our downstream sites. And there's not actually that much difference in the magnitude of water level change between these four sites where we've assessed. The key difference is that the type of regime, the erratic nature of the change in water level, and potentially also velocity at the sites. So one of the other things that comes out of it, the work that we've been doing, is trying to understand how much of a change in water level you can actually achieve. So this schematic at the top is our sites. Plot at the bottom is the date. So this is from January 2013 through to January 2016. And I've applied an offset. So these are water levels at the structures. I've applied an offset to this data simply so that the levels line up on the plot so that they're not scaled out, because water levels change as you move down the river. So these are actual the proper data. I've just so they line up on the axes. So the grey line shows water level at Lock 3, which was held stable, and the red line shows the change in water level at Lock 2. And this event here and this event here are weed pool manipulations. And so the weed pool manipulations are clearly reinstating some variability in water level at the site. This overlay shows modelled natural variation in water level. So again, I've applied an offset so that these line up over the top of each other. And what you can see is that although in the red line there is some variation in water level, it is a very small proportion of the natural change in water level that would actually occur under pre-regulated conditions. The change in water level here is about 2 metres, and the change in water level here is about 3 metres. So that half a metre change is a small fragment. And so this is kind of, in one way, could be seen as disheartening, saying, well, there's no way that we can reinstate a 3 metre change in water level at the weirs. However, this time series, so this is a little bit extended, so this is from 2009 until 16. The black line again is the modelled natural change in water level, and the blue line is the change in water level downstream of Lock 3. So this is currently recorded conditions. So what this data suggests is that if you had a regime that included weir pool lowerings and weir pool raisings, you could actually reinstate the natural change in water level at this site quite easily. Half a metre to 1 metre change in water level, like a decrease, a weir pool lowering in the magnitude of half a metre, combined with weir pool raisings, would actually reinstate the natural variation in water level at this site and be a major ecological outcome. Am I going for time? So one of the other things that we're looking at is, and Sanjina touched on this, is changes on ecosystem metabolism. So Lock 5 had a 0.45 metre weed pool raising last year. And in this event, we measured dissolved oxygen upstream and downstream of Lock 6 to see if there would be any changes in productivity that we could detect from the weed pool raising. We're using the increases in dissolved oxygen during the day as a signal of gross primary productivity, and the decreases in dissolved oxygen at night as a signal of ecosystem respiration. So these two plots along the bottom, so this is from August through until February 2016, and gross primary productivity on the y-axis. And the black line is water level. So this plot over here, this is upstream of Lock 6 where water levels remain stable. And you can see that early in this phase, productivity was fairly stable. It was a little bit bouncing around, but there was no real change in productivity with this stable water level. On the other side, this is 1168, is our site downstream of Lock 6, and water levels increased by about 70 centimetres at this site in association with that 45 centimetre weed pool raising. What you can see is that there was an increase in gross primary productivity that coincided with the weed pool raising. So this is suggesting that gross primary productivity at this site was stimulated by the weed pool raising. The second set of plots that I've just overlaid on the top is ecosystem respiration, same sites, and you can see that during this early period where water levels were stable at Lock 6, there was very little variation in ecosystem respiration, but at our downstream site where water levels changed, ecosystem respiration increased pretty much at the same time as water levels increased. So we can interpret this as saying that weed pool raisings are definitely stimulating productivity in the river channel, which is a good thing. So the missing piece is, well, the data is basically showing that manipulations of water level can certainly reinstate these processes that are primarily driven by inundation. The big ecological challenge and the management challenge is, what about those processes that are driven primarily by flow, and what about the processes that are driven by interactions between flow and inundation? They are the people to work out and try to find a way to reinstate. Thank you.